Now, so now that we've reached at least 500 micron, I'm going to start closing things off in the same way that I turned it on in the first place. In reverse. I'm going to close off both my hoses here. I'm going to close off this hose here. Make sure my gauges are totally shut. Come back here, close off my blank off valve, and only now can I turn off my vacuum pump. You do it in that order. That way there's not a negative pressure sucking oil out of that vacuum pump. Some vacuum pumps do have a check valve to help make sure that doesn't happen, but this is the safest way to do things so you don't run into an issue where oil migrates up your hoses into your gauges. Take that off, grab my cap off the back of there that's nice and safe and clean, and I didn't lose it. Get on there. Okay. There it is. So it's been about 10 minutes, and we're currently right around 650 micron. So we're going to say it's good. It has passed our decay test. I'll take a note of those numbers. In the meantime, while it's doing this decay test, I'm going to throw my tools back over here. Make sure caps are back on so it's not getting dusty inside. Wrap things up nicely. And now I'm ready to recharge my system. When you go to recharge your system, there's a couple things you have to know. Number one, what refrigerant are you putting in there? Number two, how much refrigerant are you putting in there? So, what refrigerant? This system is set up to run on my label 404, 448, and 449. The most common refrigerant is 404A. So that's the one that we're going to be using. The metering device also has to be set up for that same refrigerant to work properly. When we go to do our startup, we're going to be introducing refrigerant through this hose that's evacuated already or purged into my system. Because this is a near azeotrope, that's a special word that means almost perfect mixture, we want to charge it in a 100% liquid state. So you can't charge in a vapor state, so we have to use the liquid side. So to do this, there's one thing I don't want to do, and that's introduce any liquid into my vapor side. Any liquid that goes into our vapor side can get caught up inside the cylinder, go through the piston, and since liquids do not compress, cause damage to the valves and the piston. It can even wash out the bearings, even if it doesn't get that far. You can have liquid washout or liquid fatigue on any bearings and surfaces. It's all bad news. So because I'm charging with liquid, because it's a 400 series near azeotropic refrigerant, I'm going to be charging directly into my liquid side. That way, no matter what, this is definitely going to be 100% liquid, only where it belongs. The second step that we have to know is how much refrigerant does this system need? Some systems will tell you. They'll have on the nameplate data, this system should be charged with this many pounds, this many ounces of refrigerant. Some systems, however, give you no information whatsoever. So for those, you'll have to kind of know what you're doing. There's a way to estimate or get you in the ballpark of the refrigerant amount you need. That's going to be off of this receiver size. Receivers should be capable of holding all of the refrigerant at any point in time and only being filled to a maximum of 80% capacity, just like recovery cylinders. So, if I remember my calculations on how to do the volume of a cylinder, I can measure this out, about 3 inches wide, about 6 inches tall, do my calculations for volume, times that by 0.8 to get 80% volume, and then times that weight of water by the specific density of that refrigerant. That'll get me ballpark. At that point, then we use our measuring devices, so our electrical meter, our gauges, and our thermometer to make sure that it's running perfectly. So we're going to do that now. I've estimated this to be roughly 2 pounds of refrigerant. So I'm going to start at the low side of that. I'm going to charge this up to about 1 pound, 10 ounces. I'm going to open my cylinder here. I'm going to turn on my scale and zero it out. So it is now sitting at exactly 0 pounds, 0 ounces. Mid-seat this valve, it should be mid-seat already. This one should be closed. Like this. All right. So at this point, I'm going to scale in. I'm going to watch that. I'm going to get 1 pound, 10 ounces. So with this, it's set to 0.0 ounces. I'm going to hit my button in the middle to change the pounds and ounces. Be more exact. And I have liquid flowing in here. Watching that scale, I'm just going to see it rise. I'm going to shut this off just before I get to 1 pound, 10 ounces. So I'm at 14 ounces, 15 ounces, 1 pound. Starting to slow down now. Now the pressure in that tank is close to the same pressure that's in this system. So it starts to slow down a bit. Won't go as fast. Valves are wide open, it's still going up. Perfect. I'm now at 1 pound and 4 ounces. I'm going to call it there for a second. There is some refrigerant in here. It may be a bit low, but I'm going to get this started up. I can start with it a little bit low and slowly needle in the right amount of refrigerant. So I'll show you how to do that. Number one, most important thing, this magnet has to come off that solenoid valve before we start up. And this solenoid valve has to go back in place. This is a coil that uses electricity to make a magnet. If there's nothing inside of here for that force to act on, it is then an inductor that just creates heat. So if you start this without that on that solenoid valve, it will melt that. You may notice I left my micron gauge on there. This micron gauge is capable of handling up to 800 psi. So I know that that one is safe to keep on my system until I'm ready to take it off.
And the refrigerant won't contaminate it at all?
Refrigerant will not contaminate it. It does not care. Oil will, which is why it's in an upward fashion. So even if a little bit of oil passes by, it won't jump up. All right, so we've got 1 pound, 4.75 ounces in here. I'm gonna plug this in, start the compressor, and start it running so we can finish our charge and start it. It's my on switch. The startup procedure for this unit, it's going to take a minute before it starts. This is an anti-short cycle delay. It's often noted on a thermostat, ASD. That anti-short cycle delay, just make sure it's not starting and stopping, starting and stopping, starting and stopping, causing extra wear on the system. That could be up to 10 minutes. It could be as short as 10 seconds. So this one just started. Our solenoid got pulled in. So now it's doing its job. Refrigerant is starting to move throughout the system. Our controller up here is said open the EEV. And this pressure switch has now turned on the compressor. So it's starting to run. So compressor is running, condenser fan's going, evaporator in here is going. It's all running. At this point, during our startup process, we want to have our doors shut. And we're going to get this down to about the right temperature for this to run at. You cannot finish your actual startup until the conditioned space, in this case the inside of this box, is near the correct temperature to be running at. So as that runs, we can see this is right around 55 psi on our low side, just over 200 on our high side. You're going to check that against your pressure temperature charts. You might have a paper one. I like to use an app because it's nice and fast. I'm going to look up R44A, 4. And I'm going to check my condenser pressure versus temperature relationship. That is currently at 220, meaning my saturated refrigerant temperature in here is about 95 degrees Fahrenheit. A general rule that you can use is somewhere between 20 and 30 degrees above ambient for your condenser to make sure that it's running effectively. So if our shop area right now is roughly 70 degrees Fahrenheit, I'd want my condenser saturated temperature roughly 100 degrees. So I'm pretty close there, I'm pretty happy with that. My low side pressure, I can check that again. It's cooling down in there. So I'm going to check that pressure now. It's about 45 psi. 45 psi is going to be right around 10 degrees Fahrenheit. Again, the inside of that coil has to be a different temperature than the space around it to make it cool off. Sorry.
For that's on the Dan Foss app, right?
Yes.
Would we have the dew slider turned on? Like on
Sorry.
the dew slider? Does that matter?
No. You can turn that on. Sorry, Andrew, question?
Just to get me a little bit of an idea, what are you currently doing right now?
This is startup, so this is the last step of those 5 steps of refrigeration. Now, thankfully, Cole's taking video for everyone to review. So he'll send that to me and I will edit it and put it up for everyone to watch through.
Messiah.
So, as this pulls down to temperature, we're then going to bring out one of our most useful tools, the thermometer. This thermometer is going to tell us a lot of information about how our system is running and how well it's doing its job of changing temperature in the refrigerant, getting it into our subcool and superheated states. First step, I'm going to check my subcooler. That has already reached temperature. It's already 34 degrees in there, nice and frosty. That's working really well. Because that runtime wasn't quite long enough, I'm now going to crack this open to allow a tiny bit of warm air into that box, giving me an extended runtime. It's not going to make it work harder. It's just going to make that runtime a little bit longer by cracking the door open, not wide open.
Is that just to force it to start more gradually instead of abruptly?
It forces it to stop less rapidly. So when this pulls down to temperature, it turns off the compressor. So I want to have it run for a longer time so I can make more notes. Run times should not be 5 minutes. Run times should be longer. We want run times roughly 60 to 80% of our actual day. All right, let that heat back up. It's now warm enough to turn back on, but it's under that same delay cycle, anti-short cycle delay. It's going to wait before it starts up, so we don't have short cycle.
So those numbers are just indicating the temperature?
This is the temperature inside the box.
Cool.
So this still doesn't have all the refrigerant in it.
Nope. Looks like I have, wow, that changed. I had 1 pound and 4 ounces in there. That scale is a little bit funky. It says 0 pounds when it says 5 ounces, which is not right. It has roughly 1 pound, 4 ounces in it. I wanted a little bit more than that. I know that for a fact. But to check on that, I need this running, and we're going to take 2 measurements. I'm going to check my subcooler directly after the condenser. So once the refrigerant goes through the condenser, does those 3 things, de-superheats, gets rid of all the heat above its saturation point. Goes through its latent heat exchange. So that goes through all the heat exchange of its saturation temperature within the PE diagram. And then gets a little bit, becomes a liquid and gets a little bit cooler on top of that. we want to see roughly 10 degrees of subcooling right after the condenser. If you have anything like a receiver or head pressure controls, that can affect your measurements of subcooling. So make sure you're taking this temperature before any of those, directly after your condenser.
If you can't find the outlet for the condenser, could you use one of the loops that is near the end?
Yes, but it'd be preferable to always use the pipe coming out of that condenser. The other temperature we need to take is the superheat. The superheat is right after the evaporator coil. For anything like a TXV, it's going to be exactly where the TXV bulb sits on the pipe. That's where you're going to measure superheat. For an EEV, there's going to be a temperature sensor or a thermistor strapped somewhere to the outlet of that pipe. That's where you'd be checking that. It's usually right at the outlet of that evaporator. Try not to take superheat way up here, right before your compressor, unless you're doing an entire system drawing for your PE diagrams.
Is that because it will continue to gain superheat as it travels to and through the compressor?
Yes. Every foot of piping can get extra superheat into it, especially if this piping is very long, the insulation is damaged, or it's going through uninsulated or warm spaces like boiler rooms or up on top of roofs in the sun. So always take your temperatures right after the coil when possible for superheat and subcooling. Once this starts back up again, it's still waiting on this anti-short cycle delay, sorry. Should change that back to like 10 seconds. I can't do anything about this. It'll take me like 5 minutes to adjust that.
Quick question. So, I'm not totally certain. The evaporator is the one that's below?
Yeah.
Okay, and the condenser is the one that's, okay.
All right, so this has just clicked over, opened this solenoid, our suction pressure is rising. That has clicked on, it's turned our compressor on. Now we can check our subcooling and superheat. So what I'm doing is I'm putting my thermostat right on the outlet pipe of our condenser to check my subcooling. What I want there is to read the temperature difference between my saturated pressure in here, which was about 95 degrees, and the actual temperature of the liquid leaving this, which I'd like to see somewhere around 85 degrees. That would be an appropriate subcooling. When possible, you're going to put insulation over the top of your thermistor or your thermometer like this to make sure you're only reading the temperature of that pipe, not the surrounding air. There's also clamps that you can get that clamp directly to the pipe and give you a more accurate temperature reading.
That looks like one of those temperature readers you would stick in your chicken breast.
Yeah.
Like that looks like it's for culinary.
So this is still going up. Subcooling's a bit low. My pressure's really low on my low side. I need a little bit more refrigerant. So in this case, now I'm going to be needling in a tiny bit of refrigerant, liquid refrigerant, but I'm going to be putting it into my low side of my system. Now this is a dangerous operation because I just said never put liquid into the suction side because we could damage, wash out the bearings or damage the pistons. So to do this, you come down here, I'm going to use my gauges, there's even a sight glass here, to make sure that I'm getting nothing but vapor by the time it exits my hose. So I'm going to be the metering device right here, slowly introducing a tiny bit of refrigerant into my low side of my system. Come over here, zero this back out. Now I put 1 pound and 4 ounces in. I know, now that I've done all my calculations, I want about 2 pounds of refrigerant in this system. So I keep this one open. I'm going to barely crack this open. And what you can see when you barely crack this open in this sight glass is a tiny bit of liquid about halfway up. That tiny bit of liquid means that we're not 100% liquid by the time we're leaving. If you're worried about it, you can turn off the service hose for your refrigerant and watch that boil off entirely to the point where you have no liquid left in there. While I'm doing that, I want to be checking on my gauge over here. So I'm at 3 ounces extra that I put in there. I want to get that number up to about 12 ounces. So I'm going to slowly introduce this refrigerant in there. Again, very, very small measurements just to barely needle that in. I'm watching my gauge to make sure I'm not rising too fast. Watching this to make sure I don't have a solid column of liquid going into my compressor. And I'm watching my pressures on my screens to make sure, or on my gauges to make sure they're not too high all of a sudden. I have now gotten to about 12 ounces in there. That gives me a total charge in this system of roughly 2 pounds of refrigerant. Now we'll go through and do these same things, write all my notes down. I want to know what my superheat is, what my subcooling is, what my pressures are. And I'll jot all those down for my start report.
If you were to take this refrigerant out, like all of it, and the next guy was to come, and you were to write 2 pounds down, did he just come in and put 2 pounds in, not even have to do all this? If you reported it, said 2 pounds is the perfect amount?
It would be easier because he could just throw 2 pounds in it and start it up. But he'd still want to go through the process of writing things down to make sure that no other issues occur during that system startup.
But you would need to needle it in using the manual blending gauges.
No, you just use the active recovery method, push 2 pounds of refrigerant directly into your receiver. Okay, call it good.
As a rule of thumb, though, you might just want to stay with the course because you're at that point you're putting your faith in someone else, and you don't know if they fucked up somewhere along the line.
That is very true. Also, the other thing that can come up, and does come up quite often, when you're doing a repair on a system, it failed for a reason. Sometimes that reason is very apparent, sometimes it's not. And it's already come down again. So, in the case where you don't know what caused the failure, especially like a compressor, this startup procedure is going to let you know what killed that compressor. Is the solenoid staying open too long? Do you have valves that are shot somewhere else? Is your metering device letting way too much through or throttling? Those are all things that can take out a compressor, and you'll only find out once you do your startup procedures. Yep.
So when you do the startup procedures and get the values for it, that's when you would use that enthalpy chart to kind of get a gauge of what's going on.
Exactly.
That thumb chart, no?
With all the notes that we're taking on the pressures and the temperatures, the superheat and subcooling, we're going to chart a PE diagram, pressure enthalpy diagram. And that'll tell us the overall health of that system, and in complex problems, help us diagnose. So now that we've fully charged our system and have written down all the information we need, now the last step is going to be, I need to take all of my hoses off without losing any of that refrigerant that I've charged to the system. So here's our last step that's really important. I want to fully empty all of my hoses and safely. So I'm going to do what's called a cross purge. Look over here, I'm going to turn off my cylinder. I still have 300, 400 psi in this hose, liquid refrigerant. And right up here, I still have 200 psi of liquid refrigerant in this hose. But on my low side, the low side's sitting pretty close to 0. So I'm going to introduce all that refrigerant into my low pressure side, shutting things off so that I don't lose any refrigerant when I take my gauges off. So, just like I shut that off down there, I'm going to do the same thing here by back seating this valve all the way. It is now fully back seated. Now I can open up my low pressure side and get rid of all the refrigerant that's left in this hose. The pressure shot up to about 50, and now it's back down. Now very slowly do the same thing here. Slowly crack this open, get rid of all the pressure that's left in this side of the hose.
Looks like the system's also reacting in response to that. Does that
Yep.
just happen, or is that just
So I
coincidence?
raised the pressure until this pressure switch closed, bringing the compressor on, getting us back into that pump down.
Cool.
Now that I've satisfied that, I'm empty on my gauges and all my hoses. I can fully backseat right there. And when I take my hoses off, I don't lose any refrigerant at all. I'm ready to clean up, write things down. That's it. So our startup procedure basically ended right after the evacuation. Right after evacuation, I put refrigerant in, started the system, wrote down some numbers, and got my hoses off. Any questions?
This is something you would do